All right, so it seems like it's pretty easy to take two vectors and combine them to find the combined vector. But the only reason why these two examples were so easy was that all the vectors in these examples were parallel or anti-parallel. For example, in our first example, the first vector was to the east, and the second vector was also to the east. That's what we could call parallel vectors. Well, since the two vectors were parallel, we could just add these two numbers together. 5 plus 7 is 12. Then in our next example, the two vectors were anti-parallel. I hope you can see that anti-parallel means two vectors that are pointing in opposite directions to each other. Obviously, north and south are anti-parallel directions. They're pointing opposite to each other. So here we have 6 meters to the north and then 2 meters anti-parallel to the south. Well, it's actually quite easy to deal with anti-parallel vectors too. All you have to do is just basically subtract them. We went 6 meters in one direction and then we subtracted 2 meters because we were going back in the other direction. And we ended up with the idea that we were 4 meters from our initial point. So what we've seen is that it's very easy to deal with vectors that are parallel or anti-parallel to each other. Maybe though you can already see it's going to be much more difficult to combine vectors that are neither parallel nor anti-parallel. It's going to be much more difficult to combine vectors that are pointing in different directions. It turns out to be a much more challenging problem to combine vectors that are pointing in different directions. So you can see here that it's very easy to combine vectors if they're pointing in the same direction or if they're pointing exactly 180 degrees opposite to each other. Parallel or anti-parallel vectors are very easy to deal with. But any other vectors that are not parallel or anti-parallel are going to be quite a bit trickier. Well, now let's consider this situation where we have two vectors that are neither parallel nor anti-parallel to each other. So in this situation, we're starting at our initial point. Here's our initial point. And we're going 5 meters in this direction. You can see that we could characterize this direction as 30 degrees above the horizontal. So we're walking 5 meters in a direction that's 30 degrees above the horizontal. But then when we finish the 5 meters, we're going to continue to walk 7 more meters. But now we're not walking 30 degrees above the horizontal anymore. Now we're walking in a direction that's 60 degrees above the horizontal. We've shifted directions here. You can see these two vectors are clearly not parallel to each other. And now the question is again, what's our total displacement from the initial point? Well, here's the initial point. Here's the final point up here. And the question is, what was our total displacement in going from the initial point to the final point? See if you can pause the video and draw the overall vector here, the overall displacement vector, the overall resultant vector. I hope you gave that a shot. Remember that the overall vector starts at the initial point and points to the final point. The overall resultant vector is beginning at the initial point and pointing to the final point. Well, initially we were here, and finally we were here. So let's see if I can draw a vector between those 2 points. Not bad. So this vector right here represents our overall resultant. This represents our overall displacement from the initial point, going from here to here. This is the distance that we're interested in. We want to know how long this distance is. Well, I hope that you can see that this is not going to be 12 meters. There's no reason at all to think that this line over here is going to be 12 meters long. If we had gone 5 meters and then 7 meters in the same direction, then we would end up 12 meters from where we started. But if we go 5 meters and then 7 meters in a different direction, we can't be exactly 12 meters from where we started. It's really not obvious then how long this line is over here. So this is the difficult problem that physicists find themselves faced with anytime we're dealing with vectors in 2 dimensions. Most of the time, the two vectors are not going to be parallel or anti-parallel to each other. And it seems like we have a difficult challenge. How can we possibly figure out how far we've gone from our initial point? We can't just add the 5 and the 7. Well, here's where the very clever trick comes in that physicists have thought of. They've thought of taking each of the overall vectors and breaking them into components. Now, you can break vectors into many different types of components, but the components we're going to focus on mainly here are horizontal and vertical components. So let's see how it would be helpful to break our vectors into horizontal and vertical components. Well, when this person here walked 5 meters at an angle that's 30 degrees above the horizontal, let's actually try to break this vector into 2 components. Suppose that I make a little bit of a right triangle that uses this 5 meter vector as the hypotenuse. Here's our 5 meter vector as the hypotenuse, and here's the 2 legs of that right triangle. Suppose that we could somehow figure out how long these two legs were. Well, it turns out that you can use trigonometry to figure out how long those two legs are. We're going to learn how to do that in these videos. Right now, I'm just going to tell you how long the legs are. So those legs are 4.3 meters long and 2.5 meters. Again, don't worry if you don't know how to figure out these numbers. That's what we're going to learn later in these videos. For now, I'm just going to tell you that if you're walking for 5 meters at an angle of 30 degrees above the horizontal, then you're going to be going 4.3 meters to the right and 2.5 meters up. So what we just saw is that going 5 meters at an angle of 30 degrees above the horizontal is the same as walking 4.3 meters straight to the right and 2.5 meters straight up. If you go 4.3 meters to the right and then 2.5 meters up, you'll get to the same place as if you just followed this straight path of 5 meters. So this is what it means to break this vector into components. We've broken this vector into a horizontal component of 4.3 meters and a vertical component of 2.5 meters. Well, let's do the same thing for our second vector. Remember, this was the 7 meter vector. We were going for 7 meters at an angle of 60 degrees above the horizontal. Well, again, it turns out, you can see that we can draw a right triangle here that uses the 7 meter vector as the hypotenuse. And then we can write down how long the horizontal and the vertical legs are. I'll just tell you that the horizontal leg here would be 3.5 meters. And the vertical leg would be 6.1 meters. Later on, we'll see how to figure out those numbers. For now, you just have to trust me. If you walk for 7 meters at an angle of 60 degrees above the horizontal, that's the same as if you just walked for 3.5 meters straight to the right and 6.1 meters straight up. You'll get to the same point up here as if you'd walked 7 meters at an angle of 60 degrees above the horizontal. Again, don't worry about how I got these numbers. We'll learn how to get those later. Let's just take it on faith that those are the right numbers. Well, can you see now that we can see how far we had to go from the initial to the final point? For example, how far have we walked to the right? How far in total have we walked to the right? Well, first we walked 4.3 meters to the right, and then we walked 3.5 meters to the right. So how far in total have we walked to the right? That would be 7.8 meters to the right, or maybe again we might call that the east direction. Depending on your interpretation, we could call that right or east. So we can say that we walked 7.8 meters to the east. Now, why were we able to add these numbers so easily? We were able to add these because now these represent parallel motions. This is 4.3 meters to the east, and this is 3.5 meters to the east. Well, when two vectors are parallel, we can just add them directly. Well, now I think hopefully you can start to see how clever this trick is that the physicists have used. Our original vectors of 5 meters and 7 meters were not parallel, so there was no easy way to add them. But if we break them into horizontal and vertical components, well then the two horizontal components, by definition, are going to be parallel to each other, right? Because they're both horizontal. So those can easily be added. Then how about the vertical components? Well, we know we walked 2.5 meters north for this leg of the journey. 2.5 meters north, and then another 6.1 meters north for this leg of the journey. So how far in total have we walked north? Well, these two legs of the journey are now parallel again. If you walk 2.5 meters north and 6.1 meters north, ultimately you'll be 8.6 meters. 8.6 meters north of where you started. So we can say that overall we've ended up 7.8 meters east of where we started and 8.6 meters north of where we started. Again, the trick here is that the two original vectors were not parallel to each other. But their horizontal components are parallel to each other because they're both horizontal. And their vertical components are both parallel to each other because they're both vertical. Well, it's very easy to combine two things that are both vertical or two things that are both horizontal, whereas it would have been very difficult to combine these two overall vectors directly. So now we have a lot of information of how far we've gone. We know we've gone 7.8 meters east and 8.6 meters north. This diagram is starting to get a little bit messy. So I'm going to redraw the resultant vector over here. The resultant vector, remember, is going from the initial point to the final point. Well, now we know how far to the east is the resultant vector pointing. We know that the eastward component of the resultant meter is 7.8 meters. 7.8 meters to the east. And the vertical component is 8.6 meters to the north. Our vertical component here is 8.6 meters to the north. Again, all I've done is I've taken the resultant from this picture, since this picture was getting kind of clogged up and congested, I've redrawn the resultant over here without all the other little vectors. But we know that the resultant's overall horizontal is 7.8 meters to the east. We figured that out here. And overall, from the initial to the final point, we went 8.6 meters north. First 2.5 meters, then 6.1 meters, that's 8.6 meters total.